All right, let's talk about JavaScript objects. They're everywhere, right? But let's be honest, they can be a bit like the Wild West, totally unstructured and unpredictable. So in this explainer, we're going to dive into how TypeScript brings some much-needed law and order to that chaos. We're talking about its powerful object types, which can literally transform those sneaky runtime bugs into errors you catch before you even hit save.
So here's our game plan. We'll start with the why, like why even bother shaping our objects. Then we'll jump into the how with 3 different ways to define them. We'll touch on making properties optional and read-only, tackle dynamic data, and then get into the really cool stuff, extending, intersecting, and the absolute magic of generics. Let's get into it.
Okay, so first up, why should we even care about giving our objects a strict shape? I mean, what's the point? Well, it's all about catching errors early. We're talking about stopping bugs before your code even runs, long before a user stumbles upon some weird glitch. It's a shift from those silent, mysterious failures to getting helpful, immediate feedback right in your editor.
So let's really get to the heart of it with this question. What's the big deal with a simple typo? You might think, it's just a small mistake. And sure, in a tiny script, it's maybe just an annoyance. But in a big application, a single typo can become a silent, data-munching bug that is an absolute nightmare to hunt down later.
And this right here shows you exactly what I'm talking about. Look at the left. In plain old JavaScript, you pass in an object, but you've got a typo, color with a U. What does JavaScript do? Nothing. It just runs. It has no idea what color is, so it just ignores it. Your program doesn't crash, but hey, guess what? Your square isn't red. Now look at the right. TypeScript sees that and immediately throws a flag. It's like having a little helper on your shoulder saying, whoa, hold on, that color property doesn't exist. Did you maybe mean color? And just like that, a bug is squashed instantly instead of being discovered by an annoyed user.
All right, we've nailed down the why. Now, let's get into the how. TypeScript gives us 3 main ways to build these object blueprints. Let's break them down one by one. First up, we have what's called an anonymous type. You can see it right there in the greet function signature. We're literally defining the object's shape right where we need it, just on the fly. We're saying, hey, whatever you pass to this function, it has to have a name that's a string and an age that's a number. This is super handy for quick, simple one-off situations where you're not planning on reusing that exact object shape anywhere else.
But, okay, what happens when you do want to reuse that shape? You don't want to type it out over and over again, right? Well, that's where an interface comes into play. Here, we've basically pulled that shape out and given it a name, person. Now, our greet function is so much cleaner. Instead of that whole inline definition, we just say, this function takes a person. See how much more readable and reusable that is? It's a game changer for keeping your code organized.
And our third method is using a type alias. Now, if you look at the syntax here, you're probably thinking, hey, that looks almost identical to the interface. And you're right. We create a name type, person, and we use it in our function just like before. For these simple object shapes, you can pretty much use them interchangeably. But they do have some really important differences when things get more complex, and we'll definitely circle back to that in a bit.
Okay, let's get real for a second. The objects we deal with in the real world aren't always so perfectly rigid. Sometimes a property might be there, sometimes it might not, and other times you really, really don't want a property to be changed after it's set. Well, TypeScript has us covered with special modifiers for exactly these kinds of situations. It all comes down to that little question mark. Look at this Paint Options interface. By putting a question mark after expo and ypaw, we're signaling to TypeScript, hey, these two are optional. It means any object that claims to be Paint Options must have a shape, but it might have an expo and ypaw, or it might not. And that's totally fine. This is super common for things like configuration objects. We have a bunch of settings that have good default values. Now let's check out the read-only keyword. This thing is awesome because it's all about declaring your intent. When you mark a property as read-only, you're basically making a contract. You're telling other developers, and more importantly, you're telling the compiler, look, this property should never be changed after the object is created. It's a fantastic way to enforce immutability and stop those accidental, how did that value change kinds of bugs in their tracks.
So far, everything we've looked at works great when we know all the property names ahead of time. But what about those times when you don't? Think about objects that act like dictionaries or hash maps, where the keys themselves are part of the data. How on earth do you type something like that when you can't possibly list out every single key name?
Well, the answer is something called an index signature. It's a really clever piece of syntax that lets us describe the pattern of an object.
We get to define the type for the keys and the type for the values, even when we don't know the exact names of those keys.
Here's a classic example to show you how it works. This little line, index number, string, is the index signature. It's basically setting a rule for the whole object. And that rule is, anytime you use a number to access a property on this object, I guarantee you'll get a string back. You can see how this is basically describing the shape of an array of strings, right?
Now, these are powerful, but you gotta know the rules. There are a few important ones to keep in mind. First, your keys can only be a string, a number, a symbol, that kind of thing. Second, and this is the one that gets a lot of people, all other named properties in your object have to match the value type of your index signature. So, let's say your signature is key:string: number. That means you can't also have a name string property because the string name would have to point to a number, not a string. Make sense? And lastly, there's a slightly tricky rule about how number and string indexers have to relate because under the hood, JavaScript turns numeric keys into strings anyway.
Okay, so as our apps get bigger and more complex, we obviously don't want to be redefining similar object shapes from scratch all the time. That would be a nightmare. Thankfully, TypeScript gives us some really powerful tools for composing types, letting us build new shapes out of old ones. So we've got two main ways to do this. On the left, with interfaces, we use the extends keyword. Think of it just like class inheritance. Our address with unit gets everything from basic address and then just adds its own new unit property on top. Super straightforward. Then, on the right, with types, we use the ampersand, which creates an intersection. Our new colorful circle type is literally a combination. It has all the properties from colorful and all the properties from circle mashed together into one new type. So yeah, two different ways to achieve a similar goal, combining shapes.
So the big question is, which one should you use? Well, the most important difference comes down to how they handle conflicts. As this table shows, if you try to make an interface extend another one and they have conflicting properties, TypeScript just gives you an error right away. It stops you. But if you intersect two types that have a conflict, things get a little weird. It creates what's called a never type for that property, which basically means it's now impossible to create an object that fits this new type. And honestly, that subtle difference is often the key to deciding which approach is right for the job.
All right, now we're getting to one of the most powerful and maybe one of the coolest features in all of TypeScript, generics. This is the secret sauce that lets us write super flexible, reusable components and data structures that can work with any type, not just one specific type, all while keeping that amazing type safety we love.
So to really get why generics are so great, let's imagine a world without them. Let's say you want to create a box that can hold something. Well, you'd have to create a string box just for strings, then a number box for numbers, then a Boolean box for Booleans. You see where this is going, right? It's an absolute mountain of repetitive copy-paste code. It's tedious, and it just doesn't scale at all.
And here's the beautiful, elegant solution, a single generic box interface. See that type inside the angle brackets? That's not a real type. It's a placeholder. Think of it like a variable, but for types. Now, when we want to use our box, we just tell TypeScript what that type placeholder should be. We can have a box string, or a box apple, or a box of anything. TypeScript just fills in the blank for us. It's one single template that gives us infinite type-safe possibilities.
And here's the kicker, the real aha moment. You've actually been using generics this whole time, probably without even realizing it. Every time you write string array to define an array of strings, that's just a little shortcut, a bit of syntactic sugar for array of string. The built-in array type in TypeScript is itself a generic interface. It's just a container that can hold any type you want to put in it, which is exactly what our custom box was doing.
So think about how far we've come. We started with just catching simple typos, and we've ended up building these incredibly powerful, reusable, and totally type-safe templates with generics. These aren't just abstract features, They are real tools for writing code that's clearer, way more robust, and just infinitely more scalable. So the next time you sit down to define an object, I want you to think about that blueprint. Ask yourself, how can I make this thing not just work, but make it almost impossible for someone, including my future self, to use it incorrectly?